Long before telescopes or written language, astronomers mapped the heavens with stone and shadow. These Bronze Age scientists predicted celestial events with an accuracy that challenges our modern assumptions. By the end of this exploration, you will understand the forgotten methods that allowed them to turn the sky into a precise calendar. How did cultures separated by oceans independently unlock the same cosmic cycles? And what secret knowledge was lost for millennia? What does it truly mean to see order in the stars? The first astronomers did not look to the stars with telescopes, but with the rhythm of the seasons and the needs of their communities. Across the Fertile Crescent of Mesopotamia, along the life-giving Nile in Egypt, and within the ancient courts of China, a profound shift was occurring. People began to see the cosmos not as a chaotic display of divine whims, but as a grand, orderly system. They meticulously tracked the sun's journey, the moon's phases, and the wandering paths of the brightest planets. They noticed that specific stars would disappear and reappear at the same times each year, that the moon would wax and wane in a perfect, predictable cycle. These repeating patterns in solar eclipses and planetary conjunctions were not just curiosities. They were the first glimpses of a universal clockwork, the very bedrock of predictive science. To measure this cosmic rhythm, these early scientists built the world's first observatories from the very earth beneath their feet. They arranged massive stones in precise circles and rows like Stonehenge to frame the sunrise on the solstices. They erected tall, slender obelisks and pillars whose shifting shadows throughout the day acted as giant sundials, marking the passage of time with silent, stone-cast accuracy. Every observation was carefully recorded, often as notches on bone or marks on clay tablets, creating humanity's first long-term celestial archives. This was not a purely academic exercise. The entire endeavor was deeply woven into the fabric of survival and belief. Knowing when the Nile would flood meant the difference between a bountiful harvest and famine. Predicting the correct date for a planting ceremony or a religious festival required absolute precision, aligning human activity with the heavens above. This urgent, practical need drove them to a level of sophistication that we are only now beginning to fully appreciate. They had discovered the mathematical heartbeat of the universe, a regularity that transformed myth into the first language of science. One of their most stunning breakthroughs was the discovery of a celestial rhythm known as the Saros cycle. Think of it as a grand, cosmic song that repeats its chorus every 18 years, 10 days, and 8 hours. Babylonian astronomers, meticulously tracking the skies for centuries, realized that after this precise interval, the sun, the moon, and our own Earth returned to almost the exact same geometric alignment. This meant that if a solar eclipse darkened the skies over Mesopotamia, they could predict with remarkable certainty that a very similar eclipse would occur one Saros cycle later. They understood that eclipses are not random acts of the gods, but part of a predictable, repeating sequence. This was not a vague hunch. It was a hard-won mathematical truth, carefully inscribed onto clay tablets. These ancient records documented the timing, the duration, and even the type of each eclipse, building a data set that spanned generations. For the Babylonian priests and scholars, this knowledge was power. It allowed them to anticipate what their culture saw as potent celestial omens, transforming a source of potential fear into a scheduled event. This cyclical understanding represents a profound leap in human thought. It shows us a civilization that had moved beyond simply observing the sky to truly forecasting its behavior, laying the foundational principles for all of predictive science that would follow. But the Saros cycle was not the only celestial rhythm they mastered. While tracking eclipses, these early scientists faced another, more everyday puzzle. The sun dictates our year and the seasons, while the moon governs our months and tides. Yet these two cycles are fundamentally out of sync. A lunar year of 12 moons falls about 11 days short of the solar year. Left unchecked, a calendar based solely on the moon would see the seasons drift completely out of place, with winter festivals eventually occurring in the height of summer. This was a problem with immense practical consequences for planting and harvest, and it demanded a brilliant solution. That solution arrived in the form of the Metonic cycle, a 19-year period where the sun and the moon finally find their common ground. Babylonian astronomers discovered that 19 solar years and 235 lunar months are almost exactly the same length. This was a monumental achievement in celestial mathematics. It meant they could design a lunisolar calendar, one that honored the familiar phases of the moon while staying perfectly locked in step with the turning of the seasons. Every 19 years, the phases of the moon would repeat on the same calendar dates. Imagine the power this knowledge held. A priest or a village elder could look at a slender crescent moon and know with certainty that the spring equinox was precisely 14 days away. They could schedule the planting of crops or a major religious ceremony years in advance with an accuracy that would seem almost magical to us today. This was not just observation, it was true celestial engineering. The Metonic cycle stands as a powerful testament to their desire for harmony, their drive to weave the sun's steady journey and the moon's restless dance into a single, predictable fabric of time. This empirical knowledge, born from generations of watching the sky, was meticulously preserved on a medium built to last. In the heart of Mesopotamia, astronomers pressed their findings into soft clay, creating cuneiform tablets that have endured for thousands of years. These fragile-looking slabs are in fact our most durable window into the Bronze Age mind, a direct data stream from the world's first scientific revolution. They are not merely lists of events, they are systematic, organized tables of celestial data. One can trace the steady path of Jupiter, the retrograde loops of Mars, and the precise timing of lunar eclipses, all laid out in columns and rows with a methodical clarity that rivals a modern spreadsheet. The information was so precise, so reliable, that it formed a predictive engine written in stone. Among the most famous of these is the Venus tablet of Ammisaduqa. This single artifact records the risings and settings of the planet Venus over a 21-year period. It notes when the brilliant planet would appear as a morning star, when it would vanish from view, and when it would reappear in the evening sky. The tablet captures the complete, complex cycle of Venus with stunning accuracy. This was not a one-time observation. It was the result of a sustained, multi-generational project to map the rhythm of a wandering god. The data was so consistent that astronomers could use it to forecast the planet's future behavior for decades to come. Yet these tablets reveal a fascinating duality in the Bronze Age worldview. Alongside the cold, hard numbers and planetary positions, the same scribes often recorded celestial omens. A specific eclipse might be noted as a predictor of a king's fortunes, or the appearance of a comet could be linked to the outcome of a harvest. This was not a contradiction to them, but a complete system of understanding. They saw the cosmos as an interconnected whole, where the predictable, mathematical movements of the heavens were the very language through which the divine will was expressed. The science of prediction and the art of divination were two sides of the same clay tablet. This blend of meticulous observation and cultural meaning ensured that the data was collected with religious fervor and preserved with sacred care. It is this very practice that allows us today to hold in our hands the original observing logs of the first scientists, a permanent legacy of their quest to find order in the cosmos. These stone calendars were not confined to the sun-baked plains of Mesopotamia. Far to the west, under the misty skies of ancient Europe, a different civilization was encoding the same celestial knowledge into the very landscape. Monuments of staggering size and precision, like Stonehenge in England and Newgrange in Ireland, stand as silent testimony to a shared cross-continental understanding of the cosmos. The great sarsen stones of Stonehenge were arranged with a purpose that goes far beyond mere ritual. On the morning of the summer solstice, the sun rises directly over the outlying heelstone, and its rays pour into the heart of the circle, perfectly framed by the massive archways. This was not a lucky alignment. It was a deliberate, engineered event designed to mark the year's longest day with breathtaking accuracy. Similarly, the massive, grass-covered mound of Newgrange contains a long, narrow passage leading to a central chamber. For just a few minutes at dawn on the winter solstice, a slender beam of sunlight travels up this passageway to illuminate the dark, inner sanctum. This fleeting moment of light in the depth of winter was a powerful symbol of rebirth, a promise that the sun would return and the days would grow long again. Constructing these features required more than just brute force. It demanded generations of patient observation. Someone had to notice, year after year, the precise point on the horizon where the sun seemed to stand still at the solstices. That knowledge then had to be translated into an immovable stone architecture, a task that would have taken decades, perhaps even centuries, to complete. These structures were not just temples, they were colossal, permanent calendars. They anchored the community's sense of time to the most reliable clock they knew, the sky itself. The ability to predict the solstices and equinoxes with such architectural certainty reveals a society that had mastered the solar cycle. They used stone to eternalize their cosmic understanding, creating a link between the earth and the heavens that would endure for millennia. The precision of these ancient astronomers becomes truly breathtaking when we focus on a single, brilliant point of light. Venus was a special object of their fascination, a celestial wanderer that followed a rhythm all its own. Babylonian sky watchers did more than just admire its beauty. They tracked its every move with relentless dedication. They noted the exact date it first became visible as a morning star, heralding the dawn, and the moment it faded from the evening sky. These meticulous records were pressed into clay, creating a permanent log of the planet's 8-year dance. What they uncovered was a pattern of incredible regularity, a cycle that repeated every 584 days. This is the planet's synodic period, the time it takes for Venus to return to the same position relative to the Sun as seen from our own world. Once they had mapped this cycle, they held a powerful key to the future. They could predict the planet's position years in advance, knowing exactly when it would vanish and reappear. This was not guesswork, it was a forecast built on generations of data, a level of planetary prediction that would not be matched in accuracy for over 2,000 years. These Venus observations were just one part of a much grander project, a sprawling archive known as the Astronomical Diaries. Imagine a daily log that combined the movements of planets with notes on river levels, commodity prices, and significant political events. They were building a complete picture of their world, connecting the heavens above with life on the ground in a single, integrated system of knowledge. This systematic, long-term data collection is the very bedrock of the scientific method. It allowed them to move from simply watching the sky to truly commanding it, forecasting celestial events with an authority that still commands our deep respect today. While Babylonian astronomers pressed their predictions into clay on the other side of the world, a different civilization was engraving its celestial forecasts onto bone. In the courts of the Shang dynasty, the ritual of divination involved applying intense heat to turtle shells or the shoulder bones of oxen. The cracks that appeared were read as messages from the ancestral spirits, but the inscriptions carved beside them tell a far more concrete story. These oracle bones contain some of the earliest and most definitive records of eclipse predictions in human history. One famous inscription does not merely record an eclipse that has happened. It poses a direct question, asking whether the coming night would bring an event where the moon would be eaten. This was not a fearful guess, it was a confident inquiry, demonstrating that these astronomers possessed the knowledge to anticipate celestial events before they occurred. Their methods were developed in complete isolation from the Middle East, yet they arrived at a strikingly similar conclusion, identifying their own complex eclipse cycle that mirrored the predictive power of the Saros. The ability to forecast a lunar eclipse was a profound scientific achievement, but in the context of ancient China, it carried an immense political weight. The emperor ruled with what was known as the mandate of heaven, a divine right to govern that was directly linked to the orderly behavior of the cosmos. A predicted eclipse was not a terrifying omen, but a scheduled confirmation of the emperor's virtue and his harmonious relationship with the universe. An unforeseen event, however, could be interpreted as a loss of that mandate. This created an incredible practical urgency for precision. The court astronomers were not just stargazers, they were the guardians of the dynasty's legitimacy. Their accurate predictions ensured stability, proving that the emperor remained in the heavens' favor. The oracle bones thus reveal a fascinating duality, where the cracks in a turtle shell were thought to convey the will of the spirits, while the inscriptions next to them documented a rigorous scientific understanding of celestial mechanics. This parallel development in East Asia stands as a powerful testament to a universal human drive, a shared impulse across the globe to decode the rhythms of the sky and wield that knowledge to navigate the world. While Shang diviners read cracks in bone, Egyptian astronomers painted time itself onto the ceilings of eternal resting places. Deep within the tombs of pharaohs and nobles, elaborate maps of the night sky were carefully rendered, depicting 36 star groups known as decans. Each of these decan constellations would rise above the horizon just before dawn, marking a new segment of the night. By observing which decan was rising on a given evening, an Egyptian stargazer could determine the hour with remarkable precision, turning the entire vault of heaven into a vast cosmic clock face. This was a practical, elegant solution for telling time after sunset, a system that divided the darkness into manageable, observable increments. But these star clocks did more than just mark the hours, they also tracked the slow march of the year. As the seasons shifted, so too did the parade of decans, with a new group becoming prominent every 10 days. This created a celestial calendar that was intimately woven into the rhythm of life and death, its diagrams preserved on coffin lids to guide the departed through the eternal night. The true genius of Egyptian astronomy, however, lay in its connection to the lifeblood of the civilization, the Nile River. Their most critical celestial observation centered on the star Sirius, the brightest in the sky. For most of the year, Sirius was invisible, lost in the glare of the sun. But the Egyptians watched for its heliacal rising, that single, magical morning when it would briefly flicker into view just before dawn. This annual reappearance always coincided with the imminent flooding of the Nile. The link was so reliable that the new year in the Egyptian calendar was defined by this very event. The rising of Sirius was not just a pretty light show. It was an official memorandum from the cosmos, a direct signal that the waters would soon rise, depositing the rich, fertile silt that would ensure another year of abundant harvest. This was astronomy in its most vital form, a perfect fusion of celestial observation and terrestrial survival. By reading the stars, the priests and officials could prepare the entire society for the coming deluge, coordinating labor, managing grain stores, and performing the necessary rituals. They had mastered a form of cosmic hydrology, using the predictable patterns of the heavens to forecast the behavior of their world below. This seamless blend of precise observation and profound societal need created a calendar that was not merely accurate but essential, a testament to a civilization that learned to read its destiny in the stars. Centuries after the Bronze Age, a ship sank in the Mediterranean, carrying a secret that would only be revealed 2,000 years later. When divers recovered a corroded lump of bronze from the wreck, they had no idea they were holding the key to a lost world of engineering. This is the Antikythera Mechanism, a stunning artifact from ancient Greece that feels like a direct inheritance from those first astronomers. It is a symphony of precision gears, a portable cosmos made of bronze. With a simple turn of a hand crank, its dials would come to life, predicting the movements of the sun and the moon, forecasting eclipses, and even announcing the dates of the Olympic Games. This was not just a model of the heavens, it was a computational engine. Its intricate gear trains physically embodied the celestial cycles that Babylonian and Egyptian scholars had spent generations uncovering. The machine's very design proves that the Saros cycle for eclipses and the Metonic cycle for harmonizing the sun and moon were not just abstract ideas but practical tools that could be mechanized. One small gear with 223 teeth meticulously counted down the months between eclipses, while another system of gears replicated the moon's subtle wobble in its orbit. This was knowledge made tangible. The Antikythera Mechanism stands as the ultimate tribute to the predictive methods of the Bronze Age. It shows us that those early discoveries were not lost, but were instead refined, encoded, and ultimately miniaturized into a device of breathtaking complexity. It connects the dots from the standing stones of Stonehenge to the gearwork of Greece, a direct lineage of human ingenuity. This ancient computer whispers to us across the millennia, revealing a technological sophistication we never knew existed, and proving that the quest to build machines that mirror the universe is far older than we ever imagined. Behind these astronomical breakthroughs stood a powerful and enduring institution, the Temple Scribble School. Within the shadow of great Mesopotamian ziggurats, generations of priests and scribes dedicated their lives to the systematic study of the sky. Their training was intense, a rigorous curriculum of mathematics, cuneiform writing, and meticulous observation that transformed promising students into master astronomers. This was not a casual hobby, it was a disciplined, lifelong vocation. The knowledge they generated was far too valuable to be left to chance, so it was carefully encoded onto clay tablets and stored in vast temple libraries, creating a chain of data that could span centuries. This institutional framework was the true engine of their predictive power. A single observer might track the stars for a lifetime, but only a dedicated school, passing its records from master to apprentice, could accumulate the centuries of data required to spot a rhythm as long as the Saros cycle. The stability of the temple provided the essential foundation for this long-term work, offering both the resources for continuous observation and the protection for the fragile archives. For these priestly astronomers, science and spirituality were two sides of the same sacred duty. Their celestial observations guided the timing of religious festivals and were used to advise kings on matters of state, interpreting the movements of planets as messages from the gods. A predicted eclipse was not just a mathematical triumph, it was a scheduled divine communication, allowing the priesthood to demonstrate their unique role as intermediaries between the earthly and the celestial realms. This blend of empirical record-keeping and spiritual interpretation ensured that the data was collected with unwavering devotion and preserved with a sense of holy purpose. It was this unique fusion, supported by the unbroken tradition of the scribble schools, that allowed Bronze Age science to achieve a level of foresight that would not be surpassed for over 1,000 years. The true genius of these ancient astronomers lay not just in their observations, but in the mathematics they invented to explain them. They saw that the heavens did not move with a simple, steady beat, but with a rhythm that sped up and slowed down. To capture this complex celestial dance, Babylonian scholars developed a powerful mathematical tool, the arithmetic progression. This was a sequence of numbers where each value increased or decreased by a fixed amount. Imagine trying to predict the position of the moon, which appears to move faster at some points in its orbit and slower at others. They would take two known positions and calculate the intermediate points, filling in the gaps with a smooth, step-by-step progression of numbers. This technique, known today as linear interpolation, transformed their clay tablets into dynamic predictive engines. They were not merely recording where a planet had been, they were calculating precisely where it would be tomorrow, next week, or next month. Their tables for the moon's movement are a marvel of early computation. They account for its varying speed with such finesse that the predictions remain impressively accurate. This was not guesswork, it was a rigorous, numbers-based methodology. They treated the motions of Jupiter or Venus as a series of solvable numerical problems, breaking down the grand sweep of the cosmos into manageable, predictable steps. The creation of these numerical sequences and periodic functions represents one of humanity's first forays into true computational science. It demonstrates a mind shift from simply watching the sky to actively modeling its behavior with mathematics. These astronomers had discovered that the language of the universe was written in numbers, and on their fragile clay tablets, they began to translate its deepest secrets. Their obsession with precision led them to track the moon with an almost microscopic focus. This was the Lunar 3 system, a set of 3 critical timings that defined the very start and end of each month. The first measurement was the interval from sunset to moonset. On the first evening, a slender crescent might be seen. The second was the duration that this new moon was actually visible before it, too, slipped below the horizon. The third was the time from sunrise to moonset on the final day of the lunar month. These were not just random numbers, they were the essential data points for building a reliable calendar from the notoriously tricky lunar cycle. Why did this matter so much? Because declaring the new month a single day too early or too late would throw off the entire schedule of religious festivals, market days, and agricultural activities. It was a problem of both cosmic order and civic function. So, night after night, Babylonian astronomers watched the western horizon with a trained eye, measuring these fleeting moments with water clocks and careful notation. They recorded whether the crescent was thick and easy to see or thin and difficult to spot, knowing that atmospheric conditions could affect its visibility. Over generations, this painstaking work revealed subtle patterns. They learned to correlate the specific timings of the Lunar 3 with the moon's varying speed in its orbit. If the intervals fell within a certain range, they could be confident in their prediction for the next new moon. If the numbers were off, it was a signal to adjust their calculations. This system exemplifies a scientific mindset in its purest form. It was a continuous feedback loop of observation, prediction, and refinement, all dedicated to solving one of the most fundamental challenges of their time. The Lunar 3 system was not a sudden invention, but a methodology perfected over centuries, a testament to their unwavering belief that even the most subtle celestial behaviors could be understood, measured, and ultimately predicted. While the planets danced their wandering paths, the background stars remained a constant, familiar tapestry. To make sense of the celestial motions, these early scientists first had to map what did not move, creating a fixed grid against which all change could be measured. In Mesopotamia, this foundational work was preserved in a series of tablets known as mul.apin, one of the oldest surviving star catalogues. These were not merely lists of star names, but practical field guides to the sky. They detailed the dates when specific constellations would first become visible at dawn, marking the progression of the seasons with stellar precision. The catalogue organized the stars into 3 distinct paths across the heavens, corresponding to the realms of the gods Enlil, Anu, and E. This systematic division turned the overwhelming complexity of the night sky into a manageable, navigable space. By committing this fixed backdrop to memory and to clay, an astronomer could instantly recognize when something was out of place. A faint, fuzzy star that had not been there the night before, or a brilliant new light where only dimness had existed, would stand out with startling clarity. These were the comets and the nova, the unexpected guests in their orderly cosmic house. Identifying such anomalies was only possible because they had first established a deep, intimate familiarity with the normal state of the heavens. This stellar mapping was the essential first step in a much larger process. It provided the stable reference frame needed to track the moon's monthly journey and the planet's slow, looping retrograde motions. They were, in effect, drawing the lines of longitude and latitude on the celestial sphere, transforming the sky from a chaotic spray of lights into a structured, predictable domain. This act of cataloging was an act of intellectual conquest, a declaration that even the vastness of the night could be named, understood, and used as a tool for forecasting the future. The very landscape a culture called home shaped how it saw the heavens. Under Egypt's almost perpetually clear and dry desert skies, the stars shone with a brilliant, unwavering constancy. This environmental gift allowed Egyptian astronomers to map the celestial sphere with extraordinary detail, creating their intricate decan system that turned the night into a reliable, star-studded clock. They could depend on the sky's clarity night after night, making long-term stellar observation not just possible, but a natural part of their cosmic routine. Meanwhile, in the flat, open plains of Mesopotamia, the horizon was a perfect, unbroken circle. This vast, level geography was an ideal natural observatory for tracking the rising and setting of the sun, moon, and planets. Their astronomy became deeply horizon-based, focused on measuring the precise points where celestial bodies would first appear or finally vanish, a practice perfectly suited to their expansive terrain. In contrast, ancient China presented a different challenge. Its astronomers often worked under more variable and overcast skies. This atmospheric inconsistency made the nightly observation of faint stars less reliable. Consequently, their focus shifted toward the most powerful and undeniable celestial events, the ones that could pierce through cloud cover or be predicted with mathematical certainty regardless of the weather. They honed their skills on predicting eclipses and the cycles of the brightest planets, events so monumental they could not be hidden. These geographical and climatic factors were not limitations, but rather guiding forces. Each civilization developed a unique astronomical language, a set of tools and priorities perfectly adapted to its own world. The Egyptians built a stellar clock, the Mesopotamians a horizon calendar, and the Chinese a system of grand celestial prophecies. This was not a race with a single winner, but a chorus of different voices, all singing the same universal song of cosmic order, each in the key that their home environment had taught them. Their adaptive ingenuity reminds us that the path to scientific understanding is never a single road, but many trails, all leading toward the same truth. The connection between the stars and the soil was the very pulse of Bronze Age civilization. A farmer did not need to understand the mathematics of the Metonic cycle, but he lived by its results. When the priests announced the new month based on the lunar 3 observations, it was not merely a ceremonial declaration, it was a direct command to prepare the fields. The entire agricultural year, from the first breaking of the ground to the final harvest, was choreographed by the motions of the heavens. In Egypt, the appearance of Sirius was a national alarm bell. That single, brilliant star rising just before the sun did not just mark a new year, it signaled that the life-giving waters of the Nile would soon arrive. The entire society would mobilize, knowing they had a narrow window to prepare for the inundation that would deposit its fertile silt across the land. This was astronomy as public utility, a celestial early warning system that guaranteed food security for millions. The solstices served as equally critical waypoints. The summer solstice, marked with such precision by monuments like Stonehenge, indicated the peak of the sun's power and the approach of harvest time for early crops. The winter solstice, celebrated by the light entering Newgrange, was a promise of the sun's return and a signal to begin planning for the spring planting. These were not abstract astronomical events, they were the turning points of survival. The pressure to get the timing right was immense. A miscalculation could mean planting too early, exposing tender shoots to a late frost, or planting too late, leaving crops to wither in the summer heat. This agricultural necessity was the relentless engine driving the refinement of their calendars. Every improvement in predicting a lunar month or a solar year translated directly into more reliable harvests and a more stable society. The astronomers who tracked the stars were, in a very real sense, feeding their people. Their work in the temple or at the stone circle ensured that the granaries would be full, that trade would flourish, and that the community would endure. This profound interdependence between celestial prediction and earthly prosperity embedded astronomy into the cultural DNA of these early civilizations, transforming it from a scholarly pursuit into the bedrock of civilization itself. Yet these precise observations were never just a collection of cold data. The cosmos was a living, breathing entity, a divine realm where planets were not mere points of light but powerful gods on the move. In Mesopotamia, the red gleam of Mars was Nergal, god of war and conflict. The brilliant Venus was Ishtar, the embodiment of love and fierce power. An eclipse was not a simple alignment of shadows, it was a celestial drama, an omen that could foretell the fate of a king or the fortune of a harvest. This mythological framing was not a barrier to their science, it was its very engine. By weaving the movements of the heavens into an epic story of divine will and cosmic struggle, they gave their observations a profound urgency and meaning. The complex rhythm of the Saros cycle was not just a mathematical formula, it was the scheduled return of a celestial message, a pattern in the gods' conversation with humanity. This narrative structure made the vast, abstract cycles of the sky memorable and compelling. A young scribe learning his craft would not merely memorize a table of eclipse dates, he would learn the story of why the moon was pursued by dark demons and how the gods had decreed a pattern to its trials. The myth provided a mental scaffold, a way to organize and transmit an incredibly sophisticated body of knowledge across countless generations. The stories ensured that the data was not just recorded, but cared for with a reverence that guaranteed its survival. This beautiful synthesis of myth and measurement reveals a mindset where every celestial event had a dual identity. It was a predictable point in a geometric equation and simultaneously a chapter in a sacred, ongoing narrative. Their science was rooted in the belief that the universe was fundamentally orderly, and their mythology was the language they used to describe that magnificent, predictable order. Their genius for prediction culminated in a set of documents known as the Goal Year texts. Think of these as an ancient astronomer's personal almanac, a collection of past observations used to forecast the future with remarkable precision. The method was brilliantly straightforward. If a priest wanted to predict a lunar eclipse expected in a specific goal year, he would pull a tablet from the archives detailing the celestial events from one Saros cycle earlier. He knew that the basic pattern would repeat, but he also understood the subtle differences. The eclipse might not occur at the exact same hour or be the exact same type, so he would apply small, known corrections to the old data. This was not a theoretical model of the solar system. It was a practical, data-driven system built on the unshakable belief that the cosmos operated on a grand, repeating schedule. The entire process relied on the temple's vast libraries, those centuries-deep archives of celestial diaries. An astronomer could reach back 60 or 70 years, find the relevant Saros cycle, and see exactly what the sky had done. He would note the positions of planets, the timing of lunar phases, and the dates of past eclipses. Then, using arithmetic progressions, he would nudge those numbers forward to match his target year. This system allowed them to generate detailed, year-ahead forecasts for the movements of all the planets, the behavior of the moon, and the ominous shadow of eclipses. The goal year texts represent a profound moment in scientific history where long-term data was not just collected, but actively mined for future insight. It was a perfect fusion of empirical observation and practical computation, a testament to their unwavering confidence that the past truly was the key to the future. Even their most brilliant predictions were not immune to the realities of their world. A single overcast night could shroud the crucial first glimpse of a lunar crescent, forcing a calendar adjustment based on incomplete information. The finest mathematical models could still be thrown off by the subtle, long-term variations in planetary orbits that their cycles could not fully capture. We have records of predicted eclipses that did not materialize over their cities, their shadow falling just far enough away to be unseen, and of unexpected celestial events that arrived without warning. These were not failures of intellect, but the natural friction between a perfect cosmic theory and an imperfect, observable world. Each discrepancy, however, became a catalyst for deeper understanding. When an eclipse prediction missed its mark, the scribes would meticulously record the event as it actually happened, not as they had forecast. This new data point was then fed back into their vast archives, a single piece of a puzzle that spanned generations. Over time, these accumulated corrections led to the refinement of their core cycles. They developed more nuanced versions of the Saros, accounting for slight shifts in visibility, and honed their arithmetic progressions to better model the moon's variable speed. This iterative process of prediction, observation, and refinement is the very heartbeat of the scientific method. Their willingness to confront their own errors, to learn directly from the sky's feedback, humanizes their monumental achievements. It reveals them not as infallible seers, but as dedicated problem solvers, driven by an unwavering desire for greater precision. Their legacy is not one of perfect answers, but of a persistent, adaptive quest for truth, a testament to the fact that true discovery often begins not with a success, but with a thoughtful reconsideration of what went wrong. This knowledge, hard-won from generations of observation, was far too valuable to remain in one place. It began to travel, flowing along the very same trade routes that carried spices, silks, and precious metals. A caravan moving from Mesopotamia toward the Indus Valley did not just carry goods, it carried ideas. A ship sailing the Red Sea between Egypt and the Arabian Peninsula was also a vessel for celestial data. The core concepts of celestial cycles, calendar systems, and prediction methods became a shared intellectual currency, enriching every culture they touched. We can see this exchange clearly in the historical record. Centuries after the Babylonians perfected their eclipse cycles, Greek astronomers like Hipparchus eagerly adopted their precise numerical parameters. The very data pressed into Mesopotamian clay was translated and studied in the libraries of Alexandria, forming the bedrock of Greek mathematical astronomy. Far to the east, early Indian astronomical texts, known as the Vedanga Jyotisha, reveal a deep understanding of lunisolar cycles that bears the distinct fingerprint of Mesopotamian influence. This was not simple copying, but a creative fusion. Each civilization absorbed these foreign ideas and refined them through the lens of their own unique traditions and needs. The Greeks, for instance, sought to build geometric models of the cosmos, while Indian scholars wove complex mythological narratives into their calculations. This cross-pollination of knowledge acted as a powerful catalyst. When a Babylonian arithmetic progression met a Greek geometric model, or an Egyptian star clock inspired an Indian calendar, the entire field of predictive astronomy leaped forward. Different perspectives solved problems in unique ways, and their merged techniques created a more robust and accurate understanding of the heavens than any single culture could have achieved alone. This ancient global network reveals a profound truth about our species. Our drive to comprehend the cosmos has always been a collaborative endeavor, a shared project that transcended language and borders long before the word science even existed. We can now read the intentions of these ancient builders with tools they could never have conceived. Modern archaeoastronomy peers into the past through satellite imagery and laser scanning, mapping the alignments of ancient stones with the precision of a surveyor. At a place like Chanquillo in Peru, 13 towers stand in a silent line across a desert ridge. For centuries, their purpose was a mystery, but from a specific observing platform, the rising sun marches perfectly from one tower to the next throughout the year, its position marking the solstices at the ends of the line and the equinoxes directly in the center. This was not a fortress or a temple in the traditional sense. It was a sprawling, permanent solar calendar carved into the horizon. Across the globe on the island of Malta, the Ammisaduqa temple complex offers another stunning example. Its lower temple was constructed so that on the equinoxes, the first rays of the sun pierce through the main doorway and illuminate a central stone slab. During the solstices, the sunlight shifts, framing the edges of the same doorway with beams of light. These alignments are too precise, too consistent to be accidental. They confirm that these structures were engineered to be both places of ceremony and functional observatories, their architecture permanently locking celestial knowledge into stone. This tangible evidence transforms our understanding. We are not just interpreting old texts, we are standing in the same spots they stood, watching the same sunrises they watched, and seeing the same alignments they engineered. Archaeoastronomy bridges millennia, allowing their silent stones to finally speak, revealing a legacy of cosmic insight written not on clay, but on the very landscape itself. This newfound power to forecast the sky fundamentally reshaped the human psyche. Where a sudden eclipse had once plunged entire communities into primal fear, it could now be met with a sense of solemn expectation. The terror of a vanishing sun was replaced by the quiet confidence of a scheduled event. This was more than just a scientific achievement, it was a profound psychological liberation. By transforming chaotic omens into predictable occurrences, these early astronomers gave their people a priceless gift, a sense of control over a seemingly capricious universe. This shift in perception was a cornerstone of social stability. Imagine the immense power held by the priestly class who could stand before a king and his court, not with fearful speculation, but with a precise calendar of celestial events. They could announce that the moon would be consumed by shadow on a specific night 3 years hence, and when the event unfolded exactly as foretold, it reinforced their authority and the legitimacy of the ruler they served. A predicted event was no longer a sign of divine displeasure, but a demonstration of cosmic order and the ruler's harmonious connection to that order. Political systems were stabilized because the heavens were no longer a source of unpredictable crisis. A ruler could prepare his people, framing an eclipse not as a disaster, but as a planned celestial ceremony, a reaffirmation of his reign. This cultivated a more rational, less fearful approach to the world. The confidence gained from accurate celestial prediction planted a crucial seed, the idea that the universe was not governed by random whims, but by consistent, understandable principles. This psychological foundation, this quieting of ancient superstitions, was essential. It created the stable mental ground upon which all later scientific revolutions would eventually be built, turning humanity from fearful observers of the cosmos into confident participants in its grand, predictable dance. Yet the story of astronomy did not end with the Bronze Age. When we compare their methods to those of medieval European scholars, a fascinating contrast emerges. The medieval astronomer was often a preserver of knowledge, meticulously copying the works of classical Greek thinkers like Ptolemy. Their primary tool was the geometric model, a theoretical framework designed to explain the movements of the heavens through complex circles and epicycles. This was a more abstract, philosophical approach, focused on creating a coherent cosmic system. The Bronze Age scientist, by stark contrast, was a data generator. Their work was not built on interpreting ancient texts, but on the relentless, daily accumulation of observations. Their predictive power came not from geometric theory, but from the brute computational force of centuries of recorded numbers. They trusted the cycles they had empirically discovered, like the Saros and the Metonic, using them as direct forecasting tools. This is not to say one was superior to the other, but rather that they were different phases of a single, long scientific journey. The medieval period brought crucial innovations of its own, particularly the incorporation of algebraic tools from the Islamic world and the development of sophisticated mechanical astrolabes. These devices allowed for more precise measurements and calculations in the moment, but these later advances were built directly upon the foundation laid millennia before. The entire medieval enterprise relied on the raw data, the fundamental cycles, and the very idea of celestial predictability that Bronze Age observers had first wrested from the sky. Their legacy is seen in the gradual, unbroken improvement of astronomical precision over thousands of years. The medieval scholar refining a planetary table was, in a very real sense, standing on the shoulders of the Babylonian scribe who first dared to count the days between eclipses. This long arc of discovery reminds us that science is a collaborative relay race across time, where each era passes a baton of hard-won knowledge to the next. Behind the grand observatories and royal courts, a quieter, often invisible workforce helped sustain this celestial science. While the official records are overwhelmingly dominated by men, the role of women in Bronze Age astronomy was likely far more significant than the surviving tablets suggest. In the temples of Mesopotamia, the role of priestess was a position of considerable influence. These women were not merely ceremonial figures, they were deeply involved in the religious and intellectual life of the city. Part of their sacred duty involved interpreting the will of the gods, and since the heavens were the primary medium for divine messages, they would have been intimately familiar with celestial patterns. A priestess might have been the one to read the omens from a planetary conjunction, linking the cold data to its cultural meaning for the king and his people. Her interpretation could directly influence state decisions, from the timing of a military campaign to the rituals needed to ensure a good harvest. Across the Mediterranean, in Egypt, women of the highest status held titles directly connected to cosmic order. The queen or a royal daughter might serve as the chief priestess of a major deity, a role that inherently involved overseeing the calendar that governed all temple rituals and public festivals. Maintaining this calendar was a profound responsibility, requiring a deep, practical understanding of the lunar months and their alignment with the solar year. In a more domestic setting, the women who managed large households were also the keepers of agricultural schedules. They would have needed to know precisely when to direct the planting or the harvest, knowledge that came directly from the community's astronomical traditions. Their daily, practical application of this celestial timetable was a form of lived science, essential for the well-being of their families and workers. The absence of their names from the formal records does not mean an absence of their contributions. It simply means their work was woven into the fabric of ritual and daily life, preserved not on clay, but in the successful functioning of their society. Acknowledging these potential contributors transforms our understanding. It suggests that the community of knowledge keepers was far more diverse, a collaboration between the male scribes who recorded the numbers and the women, both elite and common, who interpreted, applied, and preserved that knowledge through ceremony and stewardship. This broader perspective invites us to see ancient astronomy not as a solitary pursuit, but as a deeply integrated social endeavor, where the task of reading the sky was a shared responsibility across the entire community. The proof of their methods is etched not only in clay, but in the very fabric of time itself. Modern astronomers have run the cosmic clock backwards, feeding ancient observations into powerful computer simulations. The results are a stunning validation. When researchers compare the eclipse records from Babylonian tablets with these digital retrocalculations, the dates align with an almost unnerving precision, often differing by mere hours over a span of millennia. This is not a matter of lucky guesses. It is concrete evidence that their empirical cycles, like the Saros, were genuine discoveries of celestial order. Their predictions were scientifically sound, built on a bedrock of real, observable patterns in the solar system. Yet these digital time machines also reveal the subtle imperfections in their models. We can now see the slight discrepancies where a predicted eclipse was not visible from their city, or where the accumulating error of a long cycle finally became apparent. These tiny flaws are not marks of failure but precious clues. They help us understand the practical limitations the ancient astronomers faced, the challenges of observing with the naked eye and measuring with water clocks. This modern validation does more than just honor their intellectual triumphs. It transforms their clay tablets into a unique scientific resource. That ancient data, painstakingly gathered century after century, provides a long-term baseline that is impossible to recreate. It offers modern researchers invaluable insights into the slow, grand rhythms of celestial mechanics, such as the gradual slowing of Earth's rotation. The work of those first scientists continues to inform our own, bridging thousands of years in a shared quest to map the intricate dance of the cosmos. This predictive power placed the ancient astronomer in a delicate position of immense ethical weight. Their celestial forecasts were not abstract numbers, they were tools that could shape the fate of kingdoms and the morale of entire populations. A king might use a correctly predicted eclipse as public proof of his divine mandate, a scheduled celestial endorsement of his rule. Conversely, an unexpected celestial event, or a forecast that proved incorrect could be interpreted as a sign of heavenly displeasure, potentially destabilizing a dynasty. The astronomer, therefore, carried a heavy responsibility to balance the unvarnished truth of their calculations with the potential consequences for public order. Their role was not just to observe the stars, but to advise on how that knowledge should be communicated. Announcing a coming eclipse could prevent mass panic, allowing the community to prepare for the event as a ritual rather than a catastrophe. Yet, in the wrong hands, the same information could be manipulated to consolidate power or discredit rivals. This required a profound ethical compass, a commitment to the integrity of their data while navigating the complex political currents of the court. They were among the first to grapple with a timeless question: how should scientific knowledge be wielded when it holds such direct power over human hearts and minds? This ancient dilemma echoes powerfully in our own time. Today, experts who forecast climate patterns or model the paths of pandemics face a strikingly similar challenge. Their predictions carry immense weight, influencing global policy and public behavior. The ethical considerations of how to present that data clearly, without inciting undue fear or being co-opted for political agendas, are a direct continuation of the ancient astronomer's burden. It reminds us that the power of prediction has always been intertwined with a profound duty to society, a responsibility to use foresight not for control, but for the collective good and stability. This enduring link between knowledge and ethics suggests that the true measure of a civilization's advancement may lie not just in its ability to forecast the future, but in the wisdom and compassion with which it chooses to share that vision. Their legacy is a quiet hum in the background of our modern world, a foundation of cosmic order built stone by stone and number by number. These Bronze Age scientists gifted us something far greater than just eclipse predictions or star charts. They gave us the very idea that the universe is predictable. Every time we check a digital calendar, set a watch by a satellite signal, or plan a mission to another planet, we are standing on the shoulders of those first astronomers who dared to believe the heavens followed a rhythm. Their work was a beautiful tapestry woven from three distinct threads: the meticulous observation of the natural world, the emerging power of mathematical reasoning, and the deep cultural stories that gave it all meaning. They did not see a conflict between counting the days of a lunar cycle and telling a myth about a moon goddess. For them, it was all part of the same magnificent truth. This unified quest to comprehend the cosmos is their most enduring gift. It reminds us that science and wonder are not opposites, but partners in the greatest of human adventures. The next time you find yourself beneath a clear night sky, take a moment, look past the familiar constellations, and consider the immense intellectual journey that began with notches on bone and alignments of stone. See the same stars they saw and feel the connection to that ancient, shared drive to map the unknown. We would love to hear which of their discoveries amazed you the most, so please share your thoughts in the comments. And if you are eager for more journeys into the forgotten corners of history, be sure to subscribe.